Okay, we are recording, I think. Yes, we share the slides. Where am I? Windows. Here we go. Okay, I hope you see the slide.
Yes, yes.
Good. So today is going to be easy and probably short. I don't think I will take more than an hour, maybe a little bit more. So what I want to do today are two things. One is to give you a kind of parochial view of quantum transport, some examples, mainly nice pictures about what we've done. I said parochial because I'll show mainly results that we've obtained in my group over the years, starting from work that I did at IBM. By now it's what, 16 years ago or more, and then from various students and postdoc that I had in various places. It shows the results that you can get, gives an idea of the numerical complexity that you have to deal with. These are extremely time-consuming simulations, and I will not go into the issue whether this is really necessary or not to understand realistic devices. That's a different story, and I don't know the answer. So I'll maybe review briefly the theory behind it. I'll show some results in two different situations. One is just what you have, some fun situations using a single mass, effective mass approximation, solving the quantum transmitting boundary method that we saw a couple of lectures ago, for particular geometries which are vaguely related to technologically interesting problems. Then I will move into what you can do with atomistic simulations, which is the fashion nowadays. Structures are extremely small. You cannot use any approximations for the band structure, scattering rates, and so on that you obtain for bulk materials. Actually, in many cases, you don't even know where the atoms are because of relaxation effects that you have when you pattern structures in thin layers, in nanoribbons, in quantum wires. And so that's why the use of density functional theory to get this information, and the band structure is quite crucial. And empirical pseudopotential, oops, my mistake here, typo, another one. It's used mainly to render the treatment a little more tractable from a numerical point of view. And I'll show some examples of some devices. So this is done in, talk here about using the master equation, the Pauli master equation, which is what we saw along the way to derive the Boltzmann transport equation, starting from the quantum equation of the density matrix, the Liouville von Neumann equation. And they can be used to simulate clearly ballistic transport, no problem, but the master equation part is the collisional operators, which has the same form as the Boltzmann equation form, which is valid for very short devices, which are the devices that are of interest today. So weak scattering is treated as a weak perturbation. Scattering is strong. If the device is very long, then this approach clearly fails. So this is what I'm familiar with. I have nice pictures to show some results, and this is what we're doing today, actually. So I'll show some of these results. So let me remind you a little bit. We saw at length how we can derive the Boltzmann transport equation that I showed here, starting from the Liouville von Neumann equation, making some approximations. And the Boltzmann equation, just to remind you, is valid when the device is much, much longer than the coherence length. So you are in a situation in which the electron can be viewed, approximated, treated as a packet in real space is extremely localized in space. By localized, I mean that it's a packet support which is much smaller than the characteristics length scale that you're dealing with. The width of this packet is essentially the coherence length, say of the order of a few tens of nanometers in a typical semiconductors. And It's also a very, very localized in momentum space because the energies that you're dealing with are much larger than the energy spread, momentum spread that translates into an energy spread of the electron. So the electron may have a collisional broadening of a few milli-electron volts if you're dealing with systems in which the typical electron energy is of the order of EV near the drain, or in any case, even in a source and drain, is the thermal energy for the milli-electron volts, for example. You ignore this spreading. And then the electron can be treated as a particle that has definite momentum and position, both of them viewed as the central values of the packet. So essentially you end up ignoring Heisenberg uncertainty principle. So you do then, under this assumption, assuming that you have weak scattering and assuming the famous Van Hove argument that the electrons interact with a bath or an external system which has an extremely large number of degrees of freedom that you do not keep track of. Under these conditions, assuming that the packet is very localized in space, then you can derive the Boltzmann transport equation. On the contrary, you may remember that we derive the Boltzmann equation by slicing the device into sections which are smaller than the coherence length, so the opposite limit. In each of them, we ignore the off-diagonal elements of the density matrix, and eventually we can stitch together all of these slices to derive this equation. However, in each slice, the situation is different. We can view now each slice as much, as I said, much shorter than the coherence length. So the packet looks like essentially a plane wave. It's extremely broad. So in the limit in which the device itself has a length which is much shorter than the coherence length, which means scattering is weak, the device is sufficiently short, then you recover the other class of initial states of the Van Hove arguments, for which you can ignore the off-diagonal elements of the density matrix, and you can use the master equation. So this is something that we've discussed before, the Boltzmann equation, how to solve it. We saw all of the, excuse me, the various methods. Boy, allergies, I'm afraid. So starting from the moments method, expansion into orthogonal functions, direct solutions, iterative methods, Monte Carlo, and so on. Now we're going to deal with the opposite problem, which is much more complicated. We saw also that in this situation you can use several methods, theoretical frameworks, I should say, to deal with quantum transport, from the non-equilibrium Green's functions to the density matrix in the Wigner function form, and so on. But we'll use in particular this Pauli-Master equation, which is conceptually simpler. So I remind you what we're dealing here. We're dealing with some geometry. This is the example of a one-dimensional geometry. We'll see what happens in 2 dimensions, and even 3 in some cases. We're considering extended states, traveling states, propagating states, whatever you want to call them, which are the eigenstates of the unperturbed Hamiltonian. Unperturbed, I mean you have just a potential, which is given by your boundary conditions and the solution of Poisson equation. And in this potential, you solve Schrödinger equation with open boundary conditions. So using, in this particular case, the Francis method that we saw before, which is a particular case in 1 dimension of the more general quantum transmitting boundary method, in which you consider a wave injected from one of the contacts, from the left contact on the right contact, and you propagate it through the device, solving Schrödinger equation in this potential, and looking at what is the transmission probability to this contact, the right contact, for example, or any other contacts in more than 1 dimension, if you have more contacts, and the reflection back to the injecting contact. So you have 2 classes of waves in this particular case, the red waves, which are the waves injected from, say, the source propagating towards the drain and partly reflected, and the blue waves, which are instead the waves which are injected from the drain. What you do is, just to remind you something that we saw in some detail in the past, here I'm just going to give you a bird's eye view of what we did. You consider the reduced density matrix, the electron reduced density matrix, so you essentially trace out all the phonon degrees of freedom and take them at equilibrium. You go back and solve the von Neumann equation for the density matrix. You integrate it recursively. You stop, as perturbatively, I should say, stopping at the leading order in the term which is proportional to the collisional terms that you might have, electron phonon in this particular case. You ignore the off-diagonal elements, and you end up with an equation which we call the pre-master equation, which describes the evolution of the occupation of each state. This row of mu would say how many electrons you have, for example, in this red state over here. And you see that the evolution is due to scattering in. Electrons in other state then scatter into this particular state's mu. Scattering out, electrons in state mu can scatter out to a state lambda in this particular case. In this form, before taking the infamous Van Hove limit, you still retain a memory of what happened in the past. This is the crucial thing that boils down to the molecular chaos or Storch-Thalensatz's assumption that Boltzmann used. So the collision depends on the past history of the particle. I gave you examples, for example, of scattering with many impurities, in which scattering with the second impurity is different from scattering with the first impurity, because in the case of the second impurity, you have the incident wave plus the wave which has been scattered, the component of the wave which has been scattered by the first impurity. So a knowledge of the past history of the particle at every collision is required in general. And so this does not introduce irreversibility. Then we can cap the machinery, but before doing that, we complete the collision. So we extend this integral essentially from 0 to infinity by assuming that the collision is weak enough so that we can take the limit of t goes to infinity as the coupling goes to 0, as this goes to a constant. And then you recover this master equation, in which these are just the Fermi-Golden rule scattering probabilities from state mu to state mu, and you have the usual interpretation in which the occupation of a state, I kept the two indices here. It means the diagonal elements, which represents the probability that a state mu is occupied, increases because you can have scattering from other states nu to the state mu, and decreases because you can scatter out. In addition, there is a term that describes the effect of the contacts, the interaction with the contacts, so to speak, that these are objects which are idealized as reservoirs that do their best to keep the charge neutrality next to the contact. So they absorb any particles which has been traveling through the device and exits through a contact, and they inject electrons as it is required to maintain charge neutrality, whichever form, this type in some linear form. Okay, so this is what we're going to do first. So we're going to solve, in some particular cases, Schrödinger equation in a ballistic case, so no scattering. It's a free electron with the only additional term given by the external potential. And we will use what's called a quantum transmitting boundary method, as I said, to solve Schrödinger equation with the open boundary condition expressing a wave of some given amplitude which is injected from each contact, and then we have to find out what is the wave inside the device and what are the reflection and transmission amplitudes or probabilities in this particular case for that wave. Eventually, having solved the ballistic problem, we can solve the problem with some weak dissipation, electron-phonon scattering, electron-electron interaction, electron impurity scattering that once averaged over impurity configurations becomes dissipative. You introduce ignorance of the configuration of the impurities after you're averaging. Otherwise, it's just a ballistic problem, fully reversible before taking this average. So we'll consider some of these cases. Okay, remind you that the quantum transmitting boundary method, which is an extremely powerful method, has been proposed by Lent and Kirchner way back then, some 30 years ago now. And the idea, as I said, is you have a blob, which is your device. You have some pipes or leads, which are your contacts. In this case, you have a two-dimensional device, this particular region in which you want to solve Schrödinger equation, and you have, in this example, 4 contacts. Each of them is injecting waves for a known amplitude, and the idea is to calculate what is the wave function inside the device with the boundary condition of each contact injecting waves of the known amplitude. And then, of course, you want to extract the probability that, say, a wave injected from contact 2 will be transmitted into any of the other 3 contacts, 1, 3, and 4, and will be reflected back to contact 2. And you do this in turn for every contact. Given some boundary conditions that you assign here, say Fermi-Dirac equilibrium distribution at a given chemical potential or Fermi level that you have in his lead, which is the applied bias, you can solve the general problem here, ballistic. And the method that was proposed by Lenter-Kirchner applies only in an effective mass approximation. It's complicated enough. And then you solve this in a self-consistent way with Poisson equation. After you have solved the states, you occupy them according to the Fermi-Dirac distributions of the contacts. So waves injected from contact 2 will have their own Fermi level or chemical potential associated with these contacts. You find all of the waves, some discretized form for a given set of energies which are injected into the device. You occupy them according to the Fermi-Dirac distribution of this contact. You do this for every contact at different biases in principle. You calculate the square wave functions associated to each of these waves multiplied by their occupation probability, multiplied by the electron charge, and this gives you the full charge distribution in the device. And then you solve Poisson equation, and clearly you will have to iterate. You start from a guess potential, you solve Schrödinger problem with the quantum transmitting boundary method, you calculate the charge, you find a new potential by solving Poisson equation, you solve Schrödinger equation in a new potential, and you keep going until you converge, and there are various methods. Under relaxation, which is sort of slow, there are Newton's method is dangerous because you have to be very close to the solution in order to converge, but if you do, you converge very fast. Typically, people use a mixed method, which is a mix between the Newton method and a method which has a general validity called the Broyden method, which essentially updates the derivative of the potential, which is a Jacobian matrix, at every time step, looking at the back history of your algorithm, your convergence problem, and tailors this Jacobian by guessing what the next step will be, the next potential will be, or the potential of the next iteration. Is sort of a black box. It's an algorithm which has general validity. It is used in a variety of cases, and this is usually gives you good convergence in most cases, quite fast. Okay, so this is what you use in 2 dimensions. In 3 dimensions will be just an even more complicated extension of this problem, more complicated from a numerical point of view, algebraic and numerical, but conceptually is the same. Where am I? I lost the full screen here. Okay. Lost my pointer. Okay.
Can I ask you
sure,
a question?
Please, Antonio, yes.
Okay, when you use drifted, you say the drifted Fermi-Dirac distribution at the contacts to maintain charge neutrality.
Yes.
For the potential, you still use a Dirichlet condition. The potential is fixed.
Okay, this is
because what I have seen in other occasions to use a Neumann condition for the Poisson in order to adjust the charge neutrality, to fit the charge neutrality.
The problem is the following. Here you have equilibrium. If this barrier is very high, for every injected wave, you have a wave which is reflected too, essentially, if the transmission probability is very small. Okay. So you recover essentially the equilibrium condition. If you set a Fermi level, you have states which are traveling both to the left and to the right, because those traveling to the left are the reflected waves. When the barrier becomes small, so you have a high injection situation, then you begin to lose charge. If you look at this blue wave, if there were a big barrier, it would be fully reflected. There would be no charge, no wave function, zero wave function down here, downstream. But if the barrier is small, part of the charge that you need here in order to maintain charge neutrality now is shifted downstream. So you have a situation in which, in the extreme limit of very high injection where the barrier disappears, here you have only essentially half of the charge that you need, or even less. It's a fraction of the length that you have in this flat region that you would like to be flat, and the entire length of the simulated region. This is a problem that has been known for a long time. William Fransley published a Review of Modern Physics paper in which he discussed it at length. Walter Putz did some studies for resonant tunneling diodes showing the same problem. And there are essentially three ways in which you can solve it. One is very empirical. It's actually due to some work done at University of Michigan, in which essentially they assume that the distribution that you're injecting is drifted in k-space. Of course, you must have that. What you want is current continuity. If you assume that here you have a contact purely at equilibrium with as many waves traveling to the left as traveling to the right, the current will be zero. And all of a sudden, as you enter the device, you have a current. So what they did instead is assume that the distribution in some effective mass approximation, the Fermi sphere is drifted along this direction by an amount which is proportional to the mobility, some mobility that you can assign to the contact. And this may help. So it's usually proportional to the field that you have at the interface. If you're missing charge, you're going to have a field which begins to drop down, which you don't want. If you account for the fact that the electron must have a velocity which is proportionally to the mobility times the field, then you see that you begin to shift the Fermi-Dirac distribution to the right, and you do your best to maintain charge neutrality. The second approach that I favor, which is physically, in my opinion, more meaningful, is you calculate the current and self-consistently you drift the Fermi-Dirac distribution in the contact in such a way as to obtain the same current that you have in a device. So you enforce current continuity across the boundary. And this works as the previous method up to a point. Once you have shifted the Fermi-Dirac distribution completely to the right, there are no more electrons going to the left, that's it. Then you're limited by how many electrons the contact, the source, can inject. You can have a situation in which you have source starvation. The contact does not have enough electrons or cannot provide a flux large enough to maintain the current that you want to have through the device, which may be a real effect. I think in some 3-5 devices you can approach this limit. So this is the method that I favor, and in principle Wyman extended using a moments method. You have some energy, electron energy that you have in this contact, which may become hotter at light bias if the field begins to be larger immediately, and you want to maintain continuity of that moment too, of the energy, and so on. But in order to maintain charge neutrality, this method usually works, and I like it. I like the physics. The third method, which is actually the most popular, was originally done by Walter Putz in simulating a resonant tunneling diode. At resonance, you have this problem, because now half of the charge is transferred downstream. So what he did was he increased the value of the Fermi level here, or the chemical potential, whatever you want to call it, so that the density that the electrons that are injected is equal to what you need for charge neutrality, even if now most of the charge is being transferred downstream. Clearly, you have to drift it quite a bit. It's unphysical. I mean, the device here, the contact, has a given density of states. It's kind of changing the material, the property of the material, depending on what is the current level in your device. So I don't particularly like it, but it works. Equivalently, shifting the Fermi level amounts to increasing the distance between the bottom of the conduction band here and the Fermi level. You can increase it either by moving the Fermi level up, or what is usually done, by using Neumann boundary condition, which is what you're saying. You, instead of having a potential which goes down here because you are missing charge, you enforce the field to be flat, 0, so the potential to be flat with Neumann boundary conditions. So essentially what you end up doing, since you keep the chemical potential fixed, you do the same thing that Walter Petz did. You increase the distance between the bottom of the conduction band and the Fermi level. And this is what typically people do because it's much easier. Drifting it in a self-consistent way, it's another self-consistent iteration that you add. With Neumann, you do your best to maintain charge neutrality near the contact. But it's unphysical, so I don't like it. There's no physical justification. If there is source starvation, that may happen in reality, you miss it because you enforce charge neutrality with your algorithm. So that's my view of the problem, which is a serious one.
Okay.
Okay. You may take whatever you want. If you like the Neumann boundary conditions, that's fine. The difference is not dramatic, but again, it depends on the situation. Neumann is definitely numerically more convenient. This drifted Maxwellian or drifted Fermi-Dirac is extra computational burden, but I like it better. I have a hard time convincing my students to move from the Neumann, which they like, to the drifted Maxwellian because it requires extra coding and a little extra self-consistent loop. However, if you can do it, it's not really adding a self-consistent loop. Once you compute a given iteration of your Schrödinger-Poisson problem, you calculate the current, and then on the next iteration, you modify this term. Where is it? You modify this term, the contact term, by just drifting the Fermi-Dirac distribution. I wrote drifted here for this reason. Okay, where was I? Okay, I'll show you some examples. This is one piece of work that was done by my colleague at IBM, now retired, Steve Locks. This is a double gate FET. You see it from the top. This is actually the, I think it's the potential. What you see is, I think it's the potential, yes, plotted in this fancy way or just as a contour plot. This is the source, this is in the drain, these are the two gates, and actually one can account for gate leakage. This is QTBM at its best with 4 contacts: the source, the drain, and the 2 gates, the top and bottom gate. And you see that there is some tunneling. I think there is some silicon dioxide here, and then there is silicon, which is a reminder of the era when the gate contacts was made of polycrystalline silicon or polysilicon. So it's a model here as silicon, and you can see that there is injection to the drain, to the gate. And these are just current voltage characteristics showing the gate leakage depending on what is the gate bias and so on. Another interesting thing that Steve Locks did was to look at the access resistance, so to speak. You consider the same device, which is the central region between these two grayish vertical bars. This is the same device, but you change the geometry of the contacts. This is just straight, which is what I showed before. You can actually solve Schrödinger equation by assuming that they have an infinite barriers in this funnel shape structures, or you have instead a wider region, which Steve called the duck bone geometry. And classically, you would expect this geometry to give you the worst current because of current crowding that you may have in the contacts, and this may give you instead the best scenario, classically, because you have a bigger source of electrons. Quantum mechanically, I don't think it comes as a surprise that you have something which is exactly the opposite. In this case, you expect quantum mechanically to have strong reflections of the waves. Think of a waveguide in which you're injecting a wave and then all of a sudden you have a constrictions. So there is a discontinuity. Waves hate discontinuities. So there's going to be some virtual reflections just because of this discontinuity in the geometry over here. This will be the best case scenario. The wave just propagates, you inject it, there are no obstacles, it keeps going. And this is somewhere in between. you have a sort of a discontinuity here, but you smear it out over a longer distance by looking at this taper geometry. And this is indeed what he found. And you can see here the potential, the charge density actually that you have here, the electron density in this particular case. You see a big electron density in a straight case scenario. Here you see how the electrons try to get in, but here you see the strong reflections. This is a high density of electrons that do not make it inside the device. They're reflected back, and the density is actually much reduced compared to that case. And indeed, you see the currents. The straight case scenario gives you a better current. If you look instead at what happens classically, which is a Monte Carlo simulation, you get sort of an opposite behavior. More interesting is once you go to this sort of simulations to add surface scattering. We talked about it last time. We saw that this is the crucial scattering process that is forcing us to consider materials alternative to silicon. We have to scale the thickness of the channel in the double gate geometry. If you view this rotated by 90 degrees, this will be essentially FinFET. As you thin it, if you thin silicon, we saw that the mobility and so in general the scattering rates, electron phonon scattering rates increase linearly with the thickness of the body, and surface roughness is a killer because now the scattering probability, the scattering rate increases with a 6th power of the inverse width. And so the mobility goes down with a 6th power of the width when you're limited by surface roughness. So you can study the effect from a quantum mechanical point of view by considering this kind of randomly roughened surface. Each of these steps is the size of a silicon dioxide bond, silicon oxygen bond, so that you can have oxygen's protrusion or silicon vacancies, whatever you have in the silicon dioxide layer. You model this according to some random, but with a probability distribution or a power spectrum, which is Gaussian or exponential. Here, frankly, I don't remember what we did. And then you look at the current, the ballistic current. You inject electrons from the left and going to the right. The current, of course, since the electrons are negatively charged, is shown going the other way. But you see something very interesting. You see occasionally vortices, which are these white dots shown here, vortices that you see in a current. And this is the probability current that you can calculate from the quantum transmitting boundary method. We always had the idea, this is now very, very many years ago, of looking at the possibility that a number of vortices can determine the transmission or the resistance across this region. It looked like it goes in steps, but we never managed to do a proper job in understanding exactly how it goes. Vortices in the Schrödinger equation are usually not considered in this context. They're extremely popular, and there is a huge literature in superconductivity, quantization of flux, and so on, but not for the Schrödinger equation. It remains to be a little bit of a mystery. I'm aware only of one other publication in which they study vortices in a Schrödinger equation in transport. And these are vortices around impurity scattering, which have been observed by the group at the University of Glasgow by John Barker and co-workers. So this is an interesting example. And you can calculate the current then by simulating many configurations and then averaging them out, which is the configuration average that we saw is required for impurity scattering and for roughness scattering in order to recover an irreversible transport equation, the master equation. Another fun thing to do in which you see... Yes, please.
Yeah, I have another question. Can I interrupt you for a second?
Absolutely. Absolutely. Okay. I welcome that.
Well, it's the last lecture, so I think I'm allowed to do that.
Yes, please.
Please. What is the channel length in the devices? Because I mean, is transport already still ohmic in that regime? Because since you have all coherent effects there, coherent scattering with surface,
Yes.
it is possible that if you introduce a more realistic phonon scattering, just a small phonon scattering, a small amount of phonon scattering, the coherence gets destroyed, and all that shades that you are showing in the bottom figure probably will disappear. Okay.
You're correct. You're correct.
And that would change the transport regime, or might change the transport regime quite significantly. I guess everything depends also on the channel length.
Okay, regarding this picture, frankly, I do not remember what the channel length was. I think that typically we use something like 1.5 or 2 nanometers for the lambda parameter, which is the autocorrelation length, so the average length of these flat regions here. So view this as a nanometer. So this is probably something like 10 nanometers, maybe a little bit more. You're absolutely right about what you're saying. As soon as I introduce some intrinsically dissipative process or phase-breaking process, all these coherence effects go away. View this as something that one may look at, I don't know, roughened or buckled or rippled graphene at 4 Kelvin, something like that, in which electron-phonon interactions do not matter, and instead you're controlled by this. Graphene bilayer or a very thin monolayer of some material of current interest, measurements done at very low temperature, where the phonon scattering doesn't matter. So this was a purely theoretical exercise, and we got intrigued by these vortices, but you're absolutely right. As soon as electron-phonon interactions come in, then you destroy these effects. Are you happy?
Okay, thank you.
Yeah, these are fun experiments that can be done in the spirit of the Bohm-Aronoff effect. If you want, this is sort of a Bohm-Aronoff around each of these vortices, and you have to go to super cryogenic temperature to see them, right? If I remember correctly, actually they go to millikelvin, so they use helium-3 refrigerators to go down to those temperatures and see the coherence effects. And that's related to the question that I asked at the beginning. Do you really need quantum transport to simulate even short devices? As I said, I don't think we have any direct and convincing experimental evidence that there are observable quantum effects along the transport directions for practical devices at room temperature. You might have it for devices which have been designed to operate on quantum principles like resonant tunneling diodes. That's okay. You have clearly observation of quantization effects, but these are along, let's say, not the transport direction, the perpendicular directions, like the wave function that you set up on this layer. But along this, I don't think that we have ever seen at room temperature in realistic devices any interference effects. There was something in the 80s about ballistic diodes in ballistic devices in 3.5s, but at very low temperatures again. So you have to design a particular device to study these effects. They don't show up in your everyday devices. At least I'm not aware of any clear evidence that this happens. This is another purely speculative idea. Steve Locks decided to look at a resonant tunneling diode, but bent. So you have two barriers over here, as is shown here. Here you have EU silicon. You can think of gallium arsenide or whatever. It was convenient to look at silicon. So you have a well, and you can have resonant tunneling between this contact and this contact through the quasi-bound states in the well. And you see indeed here that at resonance you have electrons injection from this contact. They pile up in the resonant state in this well, or quantum dots, whatever you want to call it, and then they propagate out. And for the first resonance, which means when you go at this point or after this point, you're approaching the resonance with the ground state of this quantum dot, then you see this kind of characteristics. However, if you move to the second peak, which is the second resonance, then you see something interesting. You see three vortices here again. I think that this is actually something a little more realistic that one could see if one can make a pattern a device, a resonant tunneling diode this way, because this resonance is pretty resilient. Even at room temperature, you see resonances. Washed out, you have a non-zero valley current, a very large valley current because of electron-phonon interactions, which are adding a possible conduction channel. But this is something that one may observe. Whether you can observe directly these vortices, I don't know. But now you see what's happening is funny. In this case, look at just a billiard ball approach. An electron is a billiard ball. It's coming here, turning the corner, and going this way. Here, instead, it is against two bumps, and then it begins to weave back and forth in this sort of quasi-zigzag motion, getting out. So it's like a billiard ball, which is hit on the side rather than straight this way, and begins to bounce back and forth. So it's a cute thing. It gives you an idea of what you can do with this quantum transport models, this QTBM, the quantum transmitting boundary method. A student of mine extended this, looking at the same structures that Steve Locks did, but adding impurity scattering. Again, and this is a problem that relates to the question that Professor Nudi asked before. This is going to be persisting anyway, but here you see, for example, some impurities that have been added. Maybe I have this plot which is even better. Here you see some impurities. The student of mine, former student of mine, assumed a given doping concentration, and then you look at how many dopants would you have in order to have that dopant density, and then it's a small number, and then he put some of them at random in these regions, and then he took some averages of the various configurations. This is a situation that relates to what we saw before, and I mentioned it several times. You have, for example, in this case, many impurities, a wave which is incident from the left, will scatter with impurity 1, 2, 3, and 4 in that order. And the scattering with impurity 1 will be clearly different from scattering with impurity 4. With impurity 4, you have a wave which has been already totally distorted by the presence of these waves. With the first impurity, instead, you have an incident wave. There is also distortion, which is due to the reflected waves from impurity 2, 3, and 4. So you have now a situation in which scattering with each impurity is dependent on the history of the particle, which is the pre-master equation, so to speak. Again, this is a fully reversible problem. You can go back and forth in time. And indeed, you have to take a configuration average to see what happens. And in this case, he found also some current by taking the average. But the interesting thing is to look at how the impurities can be distributed. The big problem that usually one has here is what to do with the singularity. How do you mimic the impurity? Here, essentially, there are little spikes reflected, which reflect the wave. The singularity has to be screened somehow. There is a lot of work done when people try to use Monte Carlo method, in which impurity scattering was done semi-classically by treating the electron scattering with other electrons or impurities and expressing these impurities and the other electrons as spikes of the Coulomb potential. And again, you have to take care of the singularity somehow. It's a numerical problem. Anyway, these are a set of fun problems that you can do. Again, if you put phonon scattering, then clearly you will modify completely the scattering probability and the transmission probability, because you destroy the coherence in this situation. We looked at other devices more recently in which indeed what you see is a destruction of a resonant path that you may have. You may have some resonant path. As soon as you put electron phonon scattering, those resonance paths disappear. They are washed out by the dissipative scattering with phonons. If you want to go beyond the effective mass approximation, things get way more complicated. Let me just give you a basic idea, which is brute force, starting from your single electron Schrödinger equation in a crystal. So this is the lattice potential, and this is an external potential. This would be one of the potentials that we already saw. The double gate geometry, the resonant tunneling, the L-shaped resonant tunneling geometry, whatever it is. And we want to solve this equation in the presence of the lattice potential, of course. So we know that the wave function has to have a block form, but the idea is to use an envelope approximation. If you remember the equivalent Hamiltonian that we saw a long time ago with the discussion that we had with Professor Baccarani, you assume that now the envelope depends on the position, which is something that you do not have in absence of the external potential. This will be just a constant. It will be, or it will be just the the little u, the periodic component of the wave function, right? So what you do is you plug this ansatz into the Schrödinger equation, and you see what happens. You see what equations you get. And you get something which perhaps I should show it this way. If you remember, when we discretized Schrödinger equation in one dimension, we had a tridiagonal matrix, and the eigenvalue problem that you had, or the linear system problem that you had for open boundary conditions, had a tridiagonal form, which was related to the finite difference formulation of the second derivative of the Schrödinger equation. Now, the problem is that for each point, you have a variety of plane waves, of G vectors, if you wish, the plane waves which are required essentially to give you the band structure of the device. So each of these scalar, or something that object used to be scalar in solving our Schrödinger equation, now become matrices, blocks of dimensions of the number of G vectors that you need to resolve the cross-section of your device. And each line in this matrix refers to one point in which you discretize transport along your device, say a nanowire. You slice it like a salami, and in each slice you formulate your problem. You set the potential, and that's the way you discretize it along the transport direction. But in each slice, rather than having scalar, now you have blocks, which are the plane waves that you need to calculate the band structure of that slice. And then you stitch them together in this fashion. So each slice is connected to the previous and the successive slice via these matrices. These matrices are just diagonal blocks. The diagonal blocks, instead, are highly off-diagonal. They contain all the pseudo-potentials, empirical in this particular case. In principle, you can think of some density functional theory assumption. So this would be the local component of the self-consistent pseudo-potential. The problem is what to do with the non-local term, the exchange and correlation terms, and other non-local terms. So it will get extremely complicated. You would end up getting a nonlinear system. But in a particular case in which we consider local empirical pseudo-potentials, you have these blocks. The diagonal blocks are off-diagonal, and that's where the complications come in, because they can be dense. It's a structured, highly structured matrix here. And we can talk at length about several techniques that have been used to solve it very efficiently using fast Fourier transforms. But in general, this is the type of problem that you solve. So if you solve a Schrödinger equation in a device which has a given length, and you decide to discretize the length of the region, the simulation region, into 100 points, in solving Schrödinger equation in effective mass approximation, you would have a 100 by 100 linear system, or an eigenvalue problem, depending on whether your system is open or closed. Now, depending on how many G vectors you need, your system becomes of rank 100 times the number of G vectors. To give you an idea, in 111 silicon nanowires with a cross-section of 1 nanometer, you need something like 10,000 G vectors to represent correctly the band structure. So now you get 10,000 times 100, which is 1,000,000. So you get a matrix which is 1,000,000 by 1,000,000. It's a large eigenvalue problem. It's a large numerical linear system that you have to solve. So that's where the complications come in. We're not done yet. So this is just to review what we have done, or what one can do. You have these rectangular cross-section nanowires, you have the contacts, and you simulate the region by using supercells, clearly, in this particular case. So you replicate this particular device periodically in entire space, so that you can use your plane waves to simulate the simulation. If you use tight binding, for example, which is very popular, you essentially pay the same price. Here, you pay the price of how many plane waves you need. Using atomic orbitals, you pay the price in terms of how many atoms you have to simulate. So the rank of the matrix in our case is the number of plane waves to get the cross-section, the band structure of the cross-section of the device, times the number of points. For tight binding, it will be the number of atoms times the number of orbitals that you use. So in an sp3d5 star with spin, you have 20. So you would have 20 times the number of atoms. It's roughly the same. A little bit advantageous for tight binding, but not much. And the problem remains quite daunting and extremely large. So this is again the same simulation and the same structure that we had before. But now I've added one piece, which are these self-energies, sigma left and sigma right, which also appear at the right-hand side. These are exactly the same, conceptually, the same terms that express the boundary conditions, the open boundary conditions. If you remember, we called them sigmas, also using the effective mass approximation, and we had some terms which add to the first and the last term of the matrix that you have, the Hamiltonian, the discretized Hamiltonian, and also they enter the inhomogeneous term. In this case, we have injection from the left contact. If you have injection from the right contact, you would have a similar term which appears at the bottom here, of the homogeneous term, or the known term. And these are more complicated because in multi-band situation, you can also inject waves that are in between bands. So they're evanescent waves. So the energy is somewhere in between the various subbands that you would have. So in order to do that, we go through lots of complications that I don't want to talk about, talking essentially about solving the complex band structure, but let's leave it at that. Just an idea here. This is just what we saw in the past, the boundary conditions and what the sigmas are in the effective mass approximation. This is something that we saw in the past. This is the form of the wave function that you have at the first point in the device, and this is just one point outside to the left and to the right, and how you derive these terms. In a multi-band situation, it's quite a nightmare, but it has to be done. This is the result that I think I showed you before for the closed system boundary conditions, and then for the open system, you crank the machinery, and then you can calculate currents and everything you need, having solved that big linear system. Okay, so this is, let me stop here. This is a huge system. So we did some simulations and some studies using this, and clearly we are way slower than tight binding. So tight binding approximates the band structure quite significantly in some cases, but it's preferred because it's numerically more manageable. This method, the plane wave method, is just large. That's the only issue that we have. I thought, dealing with my colleague Eric Polizzi at the University of Massachusetts, of using particular methods that he developed. He's an excellent numerical guy to solve big linear system and eigenvalue problems. But eventually the idea came to a postdoc of mine now to use a different basis. Here we're using the basis of the G vectors, plane waves. The idea that this postdoc of mine, Dr. Martin van der Put, had was, why don't we, where am I? Here, in each slice of this device, why, rather than using plane waves, why don't I solve the band structure, calculate the block waves, and use as basic function the block waves that I have in each slice. Rather than 10,000, I may need 10. That is the major advantage. So immediately, using this idea, you reduce the size of these blocks from 10,000 to 10. So you can gain 3 orders of magnitude, in some cases fewer, some cases even more. 2 orders of magnitude is the norm. So you reduce the rank of the system tremendously, and you can imagine the numerical speed that you gain out of this. So the idea that he had was to use block waves in each slice. So only few of these block waves, labeled by the K point, suffice. Then you stitch them according to a finite element method. And so you reduce the matrix by, as I told you, 2-3 orders of magnitude. And now the speed of our method, which is not based on tight binding, but on full empirical pseudopotential, is comparable to what you get with tight binding. So let me skip here and show you some results. These are the same thing that we saw before. Again, this is just a repeat of what I showed. I want to get here. Okay, so what we do here now is, for example, to look at, this is a graphene nanoribbon that we simulated. What you need is the block waves in one of the cells that are used to replicate the device. By the way, in this case, you can also simulate inhomogeneous structures. Say you want to transition from a narrow ribbon to a wide ribbon, you can do that. So what you did is you expand the wave function in the block waves, and then you use shape functions, if you're familiar with the finite element method, in order to stitch together the block waves that you have in each slice. You can actually reproduce the band structure extremely well with a few block waves. In this case, for this particular situation, which is a graphene nanoribbon of armchair edge, 10 atomic lines wide, rather than having 15,000 plane waves, you need only about 100 block waves in order to reproduce correctly the band structure. And this is where the advantage comes in. So I'll show you some results. For example, we studied what happens when you have a single defect at some particular location in a ribbon along the channel, position along the channel, position along the width from edge to the center of the ribbon. See what is the effect of one edge defect. This is important because many people, particularly for quantum computing, are considering patterning devices with single atom manipulation. What happens if you make a mistake? What happens if you miss an atom as you're patterning your device? Graphene nanoribbons are admittedly a pathological case because we saw, you may not remember, but we saw that the band gap of a armchair edge nanoribbon changes discontinuously when you move, when you change the width by just one atomic line. So a single defect here is going to cause a huge change in a band structure, in a local band structure that you have in this particular position. As you move away from the edge, things get less severe. But at the edge, you essentially, if you remember the argument that I gave you about the Clark sextets, the happy sextets, the fact that each of these hexagons can be happy, meaning that each carbon atom has a double bond with the next one, already you have 3 double bonds in each sextet or not, and the topological arguments why the band gap changes according to 3 families of width, all the ribbons which are width given by a multiple of 3 of an integer, a multiple of 3 of an integer plus 1 or plus 2, you have these 3 families. So you can expect quite a significant change, and indeed, depending on where the defect is, you show the pristine devices, this is the charge density, the electron density calculated in a pristine device. In a situation in which you have an edge defect, notice how much you have perturbed the charge density here. If the defect is one line in, there's not much of an effect. It is again effect because of this claromatic effect. If you move it 2 lines in, and not much if you are right at the center. And then you can go and calculate the local density of states. This is the square amplitude of the wave functions that you've calculated injected at a given energy as a function of energy. These are the same plots that you have from non-equilibrium function, for example. And you see that you actually have resonances depending on where the defect is. And these are the transmission probabilities. Actually, these are the current energy resolved. Then you see resonances that you might have that are evident with these bright vertical red lines. The edge defect is the most important one, as I said. And okay, this is a particular case of scattering, which is non-phase breaking. The defect is fixed. It doesn't have any internal degree of freedom. You solve Schrödinger equation, essentially, which is what we've done. No master equation, no dissipative scattering of any sort, no perturbations. If you want to call this a perturbation, it's okay, although this is not necessarily a perturbation. The effect on the wave function is so strong, it changes it so much that you cannot treat this as a perturbation. Actually, we did some studies in which we accounted for the potential change caused by a single vacancy and treat it as Fermi golden rule, and you violate the assumption of perturbation theory, unless you screen it. When you screen it, things get more manageable. Okay, now just some examples about the Pauli master equation. Again, this is the master equation in full glory, the master form of the collisional operator, which is the same as the Boltzmann form, and this is just what you have from the Boltzmann operator. And then there is the effect of the reservoir. So here we're considering electron phonon scattering now. Electron phonon is treated, I think I have some equations, in a simple way. Acoustic phonons in elastic equipartition high temperature approximation, optical phonons with a single deformation potential and flat dispersion or dispersionless optical phonons, so single frequency. And we consider a device which is 5 atoms by 5 atoms, so essentially sort of 2.5 cells by 2.5 cells in cross section. And the length of the total length of the device is about 12 nanometers, 13 nanometers, and the channel is about 5 nanometers long, the gate length. And it's an all-around gate, square cross-section. The insulator, quote-unquote, is vacuum. Okay, there's no silicon dioxide, mainly because with empirical pseudopotentials, we cannot simulate silicon dioxide. Otherwise, we've been trying, but the problem is oxygen, as in many cases. So these are the expressions for the scattering rates that we used. Notice it's inelastic. This is the occupation of the states, states injected from the source. The straight line is the Fermi-Dirac distribution, so to speak, and this is what scattering does. It subtracts electrons from the states injected from the source and brings them to states injected from the drain. These are the various scattering rates that you get at various energies. And this is the plot that you see. This is in a ballistic case, and you see how many electrons are put. You actually end up changing a little bit this, but significantly, the stripes that you see here have an increased probability. And this is due to backscattering of electrons, elastic for acoustic phonons, inelastic with optical phonons. That's why you see that you have a population over here in off states, and this is in the on state. Okay, this is the same situation at a different gate bias. And you see again how many electrons are backscattered and how much the current is suppressed. It suppressed the current by almost an order of magnitude. So now you can ask, we said that the Pauli master equation is valid only when scattering is weak. Indeed, the problem is that for silicon nanowires, the smaller they are, the larger are quantum confinement effects in this tiny cross-section. If you remember the arguments that we saw for why the electron phonon matrix element increases as the thickness of a body decreases, in 2D is even more serious. You have 2 dimensions now, which you're playing with. So the amplitude overlap integral between the initial and the final wave functions will increase tremendously as the cross-section, the area of the cross-section of the device shrinks, is reduced. So in tiny nanowire scattering is very serious. And indeed, this is what you see here, a terrible effect on the current. If you do the same for graphene nanoribbons, you don't find anything similar. That actually, my mistake, that was for graphene nanoribbons. You see something, but not as much as you see here. Here you see something, but not as much as you see for the silicon nanowire. And that's because in graphene nanoribbons, the scattering with phonons is extremely weak. And indeed, the current doesn't change much. So these are the 2 examples. Okay. Any question, Professor Nudi? Or anyone else?
No, okay.
Okay, so these are the types of plots that you begin to see a lot in the literature that we have been seeing actually since, I believe that the group at Purdue with Roger Lake and Garrett Klimek were the first ones to use the non-equilibrium functions in realistic devices with a NEMO program, which used tight binding plus the non-equilibrium functions. Now, even with DFT, you begin to be able to generate these sorts of plots. They are expensive, but they are getting treatable in recent days. Is it important? Do you really need it? I'm not sure. It would be interesting, and it is something that I would like to do. It's not easy to do it semi-classically. That's the main thing. If you want to do a Monte Carlo study of such a device, you would have to account for quantization effects. So you would have to use full band also for the band structure calculated locally, and then you have to interpolate it locally. So it's not an easy thing to do. In a way, paradoxically, it is numerically more efficient to do a quantum simulation rather than a semi-classical simulation of these tiny structures in which the band structure deviates so much from the bulk band structure. Okay, I'll stop here, and I'll just give you a brief overview of what we have done. Just to remind you, as I said, whenever you want to take an exam, talking to the student that we have, and I hope somebody will be listening to the recording, you can choose a topic, and here I just reviewed the topics that we have covered. We started reviewing quantum mechanics and Hamiltonian and Lagrangian classical mechanics, and then canonical quantization. We looked a little bit at the hydrogen atom, and we've looked roughly, very sketchily, at the periodic table. Oops, again, another type of bonds, molecules, and so on. Then we moved to crystal structure, define what is a crystal, what is a reciprocal space, look at block theorem. We spent quite some time formulating the problem, starting from, let's write down the glorious Schrödinger equation for the crystal, for the electrons and the phonons, and then we've gone through many steps, starting from the adiabatic approximation, going to the Slater determinant form of the wave function, using the mean field Hartree approximation to, in a single electron picture, to look at the effect of other electrons, ignoring spin or anti-symmetrization of the electrons, considering the Hartree-Fock approximation, including the anti-symmetrization effects of the Slater determinant. We saw that in a plane wave solution, such a brute force approach doesn't work. It's just too big. The size of the numerical problem that you have to invoke, just the size of the Slater determinant is too large. So we defined the concept of pseudopotentials, and we looked at both the self-consistent way, density functional theory, in which you treat exchange and correlation effects at various levels of sophistication, and the empirical pseudopotential, in which you freeze the Hartree-Fock, and exchange and correlation potentials empirically to what it is in a particular crystal structure. We saw alternative methods rather than using plane waves, using atomic orbitals. So we saw the tight binding method, and then we used the oddball way, which is used sometimes, which is Cato-P perturbation theory. Then we studied a single electron dynamics, looking at equivalent Hamiltonian, envelope functions, and so on. Some examples: Zener tunneling, block oscillations, the Stark ladder quantization that you have in a bulk semiconductor, a very large electric field, homogeneous electric fields, Landau levels that you have when you have electrons moving in a magnetic field in 2 dimensions, and where everything started from the energy of the states associated with a dopant in a semiconductor to look at ionization energy of these dopants. We covered a little bit relativity. That's an optional thing, just to give you an idea about the minimal coupling between the electrons and electromagnetic waves that you have to derive from essentially the 4 vectors, which are relativistic covariant. And that's where we went there, and I gave you a brief idea of where relativistic wave equations come from: the Klein-Gordon for spin 0 mass particles, and the Dirac equation for 1/2 spin particles, and how this is related to graphene in a tight binding model. Then we saw what you do to use the crystal structure. Maybe we saw it before, I forget when we saw it. Crystal structure and how you calculate the band structure in low dimensionality materials, looking at supercells. We looked at thin semiconductor bodies, graphene. We looked at one-dimensional examples, quantum wires, and briefly carbon nanotubes and nanoribbons. We spent a little bit of time with armchair graphene nanoribbons even today. And then we went to the second main part of the course, which was second quantization. So how you formulate in a Hamiltonian way systems with infinitely many degrees of freedom, with a continuum of degrees of freedom, mainly fields, and how you quantize them. So the canonical quantization of fields, and we saw the example of the Schrödinger field, how you quantize electrons. Then we looked at elementary excitation in solids, starting with a simple one, which is collective excitations of an electron gas in a homogeneous background, gallium of positive charges, and then phonons, how you describe the phonons, how you derive. So dealing with the other part of the crystal Hamiltonian that we decouple from the electrons thanks to the adiabatic approximation, and we saw how to proceed with second quantizing phonons, or these vibrations and how vibrational waves and how to quantize them. We saw as an important parenthesis the dielectric response of a solid, splitting into an ionic and electronic component. The ionic response was treated at long wavelengths, looking at the resonance of ions that oscillate related to optical phonons. And for the electronic response, we saw the general Lindau formula using the random phase approximation, and we saw important limits, the Thomas Fermi screening or the Bar-Hückel in a non-degenerate case, and at low frequency, the plasma oscillation. Okay, then we went to the third part of the course, which was generalities about scattering, how to treat electron collisions with various other things, how the Fermi-Golden rule has to be slightly modified according to the fact that we're dealing with electrons in crystals, essentially the overlap factor and the sum of the G vectors that you have. And then we looked at several scattering processes or with excitations and light. So the electron-phonon interaction, the nonpolar and the polar interactions, scattering with impurities. We spend a little more time with electron-electron interactions because they're divided into long-range and short-range components. We saw impact ionization, and in general, as Coulomb effects, we saw bandgap narrowing effects. I think I mentioned more or less around that time what is superconductivity from the conventional BCS, Bardeen-Cooper-Schrieffer superconductivity theory, which because it's due to the electron-phonon interactions and effective, attractive phonon-mediated electron-electron interactions. And then we concluded looking briefly at the radiative transitions in the dipole approximations. Then we looked at semi-classical electronic transport. Probably this is the hardest part of the entire class. How do you go from quantum to classical transport using the Van Hove arguments, and how you deal with a collisional operator which takes the form that you see in the Boltzmann equation. And we looked at this in the electron-phonon case, in the case of ionized impurity, in which now it's not the large number of degrees of freedom of the system, but it is the configurational average that you're taking, and then Coulomb interactions among electrons and how the detailed balance and equilibrium forces the electron-electron interaction to give you a solution which is of a Fermi-Dirac form at a temperature which must be set by the bath. And finally, we looked at approximation method to solve semi-classical transport, looking at the moments method, with diffusion, hydrodynamic energy transport, expansion into orthogonal functions. We looked at direct solutions, the weighted particle method, matrix inversions, and then we looked at scattering matrix, the approach that Mark Landstrom devised a couple of decades ago, maybe a little bit more, cellular automata, iterative method to solve the Boltzmann equation in its integral chambers form, and then the Monte Carlo method. And finally, what would happen when you do semi-classical transport in low dimensionality system. That was of interest mainly because it justifies the reason why we have the necessity, or people are looking at materials which are alternative to silicon, the post-silicon CMOS technology, because transporting very thin bodies is strongly affected by confinement, quantum confinement effects, and I'll show you why. And finally, what we've seen today, well, last time, some approach to quantum transport and some examples that I gave you today. So this is it. It's the end of the class. I hope whoever attended it to the lectures live or recorded enjoyed it. I realize it is difficult. That's why I think that the form of the exam that I suggest, to bring a topic of your choice, will give you a little bit of a slack. You can prepare only one subject and we can discuss it. Of course, you have to be mindful because every subject is connected to the other. So there might be questions that span a little bit of everything, but at least it will be focused on one particular subject. Okay, any question, any comments, any suggestion? Oops. Okay, if not, I guess it's time to conclude. I see that there are a few more people today. That's good. Ok,
rimani lì un momento, Massimo.
Pardon me?
Rimani lì un momento dopo.
Sure, okay, I'll rimarrò. Okay, thank you very much and enjoyed your summer break, whatever it is. Okay,
ciao,
bye-bye.
Massimo.
Bye-bye, ciao, ciao.
Sentiamo.
Bye-bye.
Ciao.
Ciao.